hydrogenation by carbonaceous deposits, and we prepared our catalyst using the solgel method. So first, I want to talk about a little why this reaction is important. And to industry, polyethylene represents about 40% of the thermoplastic market, or about 45 million tons per year. Well, in ethylene feed streams, acetylene constitutes about 0.35 weight percent, and it causes problems downstream in the production of polyethylene. So industry would like to see that reduced to 5 or 10 ppm, and traditional treatment is reaction, although separation has been tried, and the typical support is palladium on an alpha alumina pellet. So the objective of our study is to prepare a homogeneous catalyst to study the kinetics of acetylene and ethylene hydrogenation. And we want to understand what the function of the reactants is in the rate expressions and the function of temperature. And we're going to study this at low conversions. So once we have our rate data, then we want to discriminate amongst rival Langer-Hinshelwood expressions and then regress the values of equilibrium and kinetic constants and then try to correlate those with any known spectroscopic data. Okay, now to the meat. Well, this reaction has been studied for a long time and by a lot of different people. And over the years, a lot of information has been found out, and a good reference for some of that information is by Professor Bond, and it's in applied catalysis. And I had to write this in because I just remembered it. But what I've tried to show here is that acetylene can absorb, and I've drawn these dotted lines to show that these arrows don't necessarily correspond to the products that I've shown. But you can get a variety of different intermediates. You might get a pi-bonded complex, or a di-sigma bonded complex, or a vanillidine, or an ethylidine, or an ethylidyne. And the problem is that any one of these, or something other than these, may be contributing to the hydrogenation of acetylene, and is the reactive intermediate. So from this, you get a variety of products. You might get butadienes, you might get cyclic C4s, and benzene, and those things can lead to green oil and or coke, and it may come from these, it may not. But important to this study is the intermediate for ethylene, and then its further hydrogenation onto ethane. Now, the role of the ethylidine isn't really known, or if it is, I haven't been able to find it, so it still may be out there. And ethylidyne is thought to contribute to the direct hydrogenation onto ethane. So the fastest process of these intermediates is thought to be this one, and it's acetylene to vanillidine, then to ethylene on the surface in some either pi or di-sigma form, and then further hydrogenation onto ethane, and this is what we'll be studying. Now, to complicate matters even further, there's been in the literature more than one route to the formation of ethylene, and I've shown these here. The reaction on palladium, and I've shown without indicating which intermediate, but acetylene on palladium might react with a hydrogen to give some kind of ethyl intermediate, which can then further hydrogenate onto ethylene. And that's just on palladium, and the hydrogen and acetylene are both thought to be competitively absorbed. But the reaction on palladium also might be coupled with a carbonaceous deposit, and this has been proposed since the late 70s. So acetylene on palladium might react with a hydrogen on palladium to form the ethyl intermediate, and then that can further hydrogenate with a hydrogen from this carbonaceous species to give, well, that should be just a Y, not a +1, to give the ethylene on the surface. So one of the most recent results is by Borzinski and Cebulski in applied catalysis, and they actually did this reaction at 25 degrees C, and they came up with 4 products. A 4-term rate expression, well, 3 products, 4 terms, and 2 is for just ethylene, 1 is to the C4 oligomers, and 1 is onto ethane. So Sommerjai has shown that this one is very small, or much smaller compared to these 2. And this is really relates to coking on the surface of the catalyst, so it's expected to also be very small. And this we show this because we wait until the catalyst reaches sort of a steady state. But these 2 terms correspond. This one corresponds to the carbonaceous deposit. And notice that there's only a 1 in the denominator, and that's because you'd have 2 terms, 2 sets of parentheses, 1 for the absorption of acetylene on palladium, and then 1 for the hydrogen transfer. And then you have this one, which is the competitive adsorption. So Porzinski and Cebulski proposed this, and what we want to find out is if our results concur with this, and two, if it's applicable to ethylene hydrogenation, if you get the same kind of result. So I want to talk a little bit about our method to solution, because the actual analysis was rather complicated, and I'd like to spend just a minute on it. But we get our rate data, and then we analyze it with respect to the dependence of the reactants and temperature. Then we propose some reasonable expressions, and then try to use any spectroscopic data to prepare estimates for the kinetic and equilibrium constants. Now, the reason we need to do that is because in the expression that I've shown previously, you have these terms sort of lumped in. The numerator has sort of a lump term, a K prime for one mechanism. Well, that can actually be broken down into its equilibrium components, shown with a large K's, for absorption of species I and for hydrogen, for example, and the actual rate constant. Well, being that these are multiplied, the activation energies are then additive. So if you can find some information about the enthalpies of absorption of acetylene and hydrogen, then you can estimate what this might be and what this might be. And that helps you in your regression. So we're going to begin with the differential analysis, and we just use a regular spreadsheet to resolve the data. But then, since this is a very, very fast reaction, some of your conversions might be higher than you expected, and we're going to clean that up a little bit with the integrated reactor design equation. And we're going to use Mathematica as a software. And since this is a calculus equation, we want to convert this into an algebraic equation so that we can use the Levenberg-Marquardt algorithm to minimize the error of the fit. And we'll do that for a variety of expressions. For our catalyst, I said that we would use the solgel method. And this is a typical preparation by Yoldis's method, 1975, in which we use aluminum sec butoxide, and we add that to deionized water for 15 minutes at 85 degrees C, and butanol is evolved. And we add HCl to peptize it. And then we let this stir overnight to form a clear solid behemite particles. And then we add our aminochloride palladate precursor. And then we heat the solution at 95 degrees C in order to evaporate the solvent and form the gel. We then calcine the gel at 400 degrees C for an hour prior to any characterization or reaction studies. So then we pulverize the gel into a fine powder for our reaction studies. So after we do all of that, we determine the catalyst characteristics, as shown here. So we use a very low weight loading of palladium, and we send this off for an ICP analysis. This is our density. It's about 2.8 grams per centimeter cubed. And after we pulverize the catalyst, we get an average diameter of the catalyst particles to be about 5 microns. You actually get a range, and I'm just showing sort of the average. The BET area is shown to be fairly high, 366 meters squared per gram, with a unimodal pore size distribution around 3.6 nanometers. We use the typical hydrogen chemisorption with a 1-to-1 relationship, and we find that the surface metal exposed is about 32%, with an average palladium particle diameter of about 3.1 nanometers. Okay. So for testing the catalyst, we use a very, very common reaction setup. We have a bank of tanks with different acetylene and argon mixtures. In order to control the composition and flow rate, we use acetylene flow meters. We use a silica frit to give good mixing before entering the reactor. And then we have a tube inside of a shell, and the shell's plugged, and there's no access to this void space. But we have this Pyrex tube. It's about 1/4 inch in diameter, and we put Pyrex wool before and after, and we put a layer of palladium gamma aluminum in between. We sandwich them. And I have a K-type thermocouple that extends down and penetrates this layer of catalyst. So then we use a gas sampling valve to send a sample to the GC, and then using a mole balance, we can calculate the extents of reaction. Okay. Alright. So before we can take any usable rate data, there's a couple of things we have to do. A catalyst being a dynamic creature that it is, you have to account for its deactivation. So we allowed 6 hours to pass and then started taking data. We took data the entire time, but after 6 hours, the deactivation rate slowed to an almost linear regime. so that I can approximate it with a constant K. And then using points before and after my rate data, I can correlate that back to the time at 6 hours. So that all my rate data is based on the same activity. The second thing you have to do is you have to account for mass transfer limitations. And on the left, I've plotted the rate of reaction. And on the bottom, I've plotted the square root of the velocity. And if you can show that these are independent of one another, then you've reached a region where there is no external mass transfer limitation. So for 3 different temperatures, we've adequately shown that. One of the problems with this being such a fast reaction is that you can't vary the weight of catalyst very much and expect to determine the internal mass transfer effects. So we use the Weiss-Prater criterion, and if you can show that it's much, much less than 1, then you can reasonably exclude internal mass transfer limitations. So by excluding external and by excluding the total, we can exclude the internal. All right. Now the second thing you have to worry about is in successive reactions. It just might have turned out that the ethylene formed from acetylene, that this reaction here, the successive hydrogenation, was the slower reaction. Now that might not make sense, but it might have been true. So one of the things I wanted to test was the effect of ethylene concentration on the rate of acetylene hydrogenation. And as you can see, they're independent. If this had been an equilibrium reaction, by increasing the ethylene concentration, you would have expected the rate of reaction to actually go down, and it doesn't. But by increasing the hydrogen concentration, you do get the expected increase in rate. So now we've shown that we don't have any equilibrium considerations, but this also says one other thing, that at least at our temperatures, that ethylene is probably not poisoning the reaction, at least these concentrations. So on to the acetylene kinetics. Now we took data from 100 to 225 degrees C, but I'm only going to show some of it because it becomes rather convoluted. And I'm just going to write down the observations. And it's interesting to note that the order with respect to acetylene seems to increase from 0 order at low temperatures to first order at high temperatures. And we can attribute that most likely to just an absorption phenomenon. As we increase the temperature, acetylene doesn't absorb as strongly on the surface, so that it appears to be first order. Now looking at the reaction of acetylene with respect to hydrogen concentration, we see something rather unusual. It appears to be first order at low temperatures and perhaps half order at higher temperatures, and this seems to be very unusual to us, and it's not an expected result. And we see this transition at approximately 200 degrees C. Now the flow rates for this are approximately 150 milliliters per minute through 6 milligrams of catalyst. So it's a very high flow rate to a very small weight of catalyst. So then we did the same thing for the ethylene kinetics. And what we have here is we have ethylene that's been spiked with a little bit of acetylene, about 0.365%. We want to study the kinetics with acetylene present in the feed. And the only interesting thing to say is that ethylene appeared to be first order over the entire temperature regime. However, one unexpected result was that the rate decreased with temperature. And I hope to explain that a little later. But versus hydrogen concentration, the rate of ethylene hydrogenation seemed to do something funny again. It seemed to go from a half order to a first order to a half order. And again, we see the decrease in rate with temperature, as in the ethylene. But this is also very unusual. We get the temperature change seems to be right around 200 degrees C for one. But we have this half order mechanism at 100 degrees C. So in order to explain these results, we at least need to test some expressions that have half order in hydrogen and first order in hydrogen over all the variety of combinations. Okay. So then I can plot all of my data versus 1 over t, natural log of the data versus 1 over t. So the slope here would be the opposite of the activation energy. So this is a positive activation energy for acetylene hydrogenation. And it appears to pass through a maximum, again, at about 200 degrees C. Now remember, that's where we saw the apparent change in dependence upon the hydrogen concentration. So this might just be an artifact and a result of bad data collection, or there may actually be something going on there. For ethylene hydrogenation, it's interesting to note that you have a positive slope, which indicates a mostly negative activation energy. Now, I had to search the literature far and wide to maybe explain why this might be possible. And this is the result of an apparent activation energy. And these are all apparent activation energies. And this would result as the absorption of ethylene being so weak that the rate of desorption is much faster than the rate of reaction. So the slow step is the rate of reaction on the surface, but the concentration available for reaction is actually decreasing very fast. So now, these are our results. I didn't bother to try to show all the different error estimates for all the different possible Langmuir-Hinshelwood expressions. I'll just say that I tried half order in hydrogen here and half order in hydrogen there, then these separately, and all the possible combinations. And you just get a table that showed a decreasing in error until you get to this one. But this expression corresponds exactly with the expression proposed by Borzinski and Cebulski. Except that we don't have a 1 over KAC plus CAC in the denominator of the second expression. And this expression corresponds to the carbonaceous deposit. And the reason that it's not here is because by the time this expression becomes important for our rate data, the absorption of acetylene becomes too weak for it to be important. So this term that you see here is actually also here. But because this doesn't actually occur until higher temperatures, the desorption is this value is very small. So here, I've deconvoluted the rate data, showing the turnover frequency on the left versus temperature on the right. And you can see that the mechanism 1, or just the mechanism involving palladium only, makes only a small contribution under our conditions to the rate observed. However, as you increase temperature, the carbonaceous deposit, the transfer of hydrogen from a carbonaceous deposit becomes more important and increases. Now this decline here, one might also attribute to the desorption of acetylene becoming faster than the reaction of acetylene, but it probably isn't true. It probably comes from this term becoming big in the denominator and starting to poison the reaction. So we're running at a reactant ratio of 8:1 hydrogen to acetylene, so we're sure that there's no stoichiometric effects. And we do all of our work at 1 atmosphere. Now that's quite a bit removed from the industrial conditions, but we're trying to demonstrate the different contributions of each mechanism. So we do the same thing for ethylene, and we get something a little bit different. As you can see, the mechanism involving the hydrogen transfer contributes very little to the hydrogenation of ethylene on the surface. The primary mechanism is just the straight absorbance of ethylene and then the transfer of hydrogen from palladium. Now, this maximum here might also have been attributed to the rate of desorption becoming faster than the rate of reaction, so much faster. But it isn't true either. As you go to lower and lower temperatures, actually, the absorption of acetylene begins to really poison the reaction and, in fact, quenches it. And these are the conditions shown for the data. Now, one unusual result is the half-order dependence in hydrogen. And as far as I can tell, or at least as far as I've explored, I can't seem to find this supported anywhere in the literature. So I guess we're proposing it. So it's interesting, but hopefully I can correlate with that something later. So if you compare the rate data, the rate selectivity is shown here, and it shows agreeably that the selectivity increases with temperature. As you increase temperature, the selectivity goes up. The selectivity of ethylene. So now, you might be interested to know how our data actually compared to our experimental error. And so what I've shown here is the relative error of the predicted result to the actual result. And as you can see that most of the points lie within 10%. So I had less than 10% error for almost every data point, except for a few which were outliers, or maybe outliers or just maybe wrong. But the average error was about 6%, and the experimental error was calculated about 4.5%. So we didn't completely account for everything, but we seem to be getting closer. So now, I went to the literature, and if you look at the two rate expressions, these are the value of the activation energies for each component of each mechanism. So this is just the competitive absorption on palladium only for the hydrogenation of acetylene. And the activation energy is low, it's about 29. But for the second mechanism involving the carbonaceous deposit, the hydrogen transfer mechanism, it's much higher, about 168 kilojoules per mole. And then you see the same trend for ethylene, that the carbonaceous deposit mechanism, the activation energy is higher than the activation energy for just the palladium only. Now I should say that when I wrote this K1, this includes both the first and second addition of hydrogens, although I can't deconvolute those, so this activation energy is actually for both steps, and there's no way of knowing how much one contributes to the total. And I should say, this is important, but the 95% confidence intervals around the activation energies is about 25%, plus or minus. That's not a trivial detail. So if you go to the literature, some of our results could be correlated. And for vanillidine, the enthalpy of the energy of desorption was found by Tysot's group to be about 115 kilojoules per mole. So I've shown in the blue up here the equilibrium constant for acetylene, and our enthalpy of absorption, the minus enthalpy of absorption, we found to be about 125 kilojoules. Well, interestingly enough, they fell within each other's error bars. So that was a nice result. So this seems to concur with the vanillidine intermediate. Now, for the activation energy on ethylene, you can actually go back to two sources, and one is Schweet's work from 1958, and you can estimate that if it's half order, and that if it's a pi bonded complex of ethylene, that the activation energies will actually match up very well. And we found 78.8, and I think if you calculate from his work, it would be about 82. And then Matthew Newrock calculated recently using Monte Carlo simulations that it should be about 83 for the pi bonded complex. So those correlate very well also. So in total, the last one is the enthalpy of a hydrogen transfer, and I couldn't find a comparative result. But for this work, it's about 135 kilojoules per mole. And notice that it's endothermic. And that makes sense because the second mechanism didn't come about until higher temperatures, so that it takes energy in order to activate this step. Well, just very quickly, this seems to sum everything up. But I have two mechanisms, and they're shown here, one for palladium only, and then one for involving a carbonaceous deposit. And the acetylene absorbs the vanillidine, reacts with a hydrogen from the surface, and then forms some kind of perhaps ethyl intermediate, which reacts with another hydrogen from the surface to form a pi complex ethylene, which can then desorb or react further onto ethane. The second mechanism involved the non-competitive absorption of acetylene and the hydrogen transfer. And hydrogen can then absorb on the palladium, and it dissociatively absorbs, maybe transferred as an add atom to a carbonaceous deposit, and then transfers on to form a vinyl intermediate, and then on to form the ethylene. So it shows you that you can get ethylene from two different directions. And this sums up pretty much the ethylene kinetics and the acetylene kinetics. Now the vanillidine is the intermediate, and possibly the pi bonded ethylene is the intermediate. So quickly, the summary and conclusions. We used a solgel prepared catalyst. This is good for kinetic analysis. The best fit with ethylene rate expression involving only palladium is approximately half order in hydrogen. We found that two parallel mechanisms exist for both acetylene and ethylene hydrogenation, although it seems to only be important for acetylene. The mechanism involving carbonaceous deposit has a higher activation energy as expected, and the regress parameters suggest that vanillidine and pi bonded ethylene are the intermediates in their respective hydrogenations. And finally, the enthalpy of hydrogen transfer from a carbonaceous deposit is endothermic as expected. So finally, the important part, and that's money. And I have to thank the Department of Energy, Basic Energy Sciences, and finally from my fellowship from the Board of Regents of Louisiana. So thank you very much, and I hope you have questions.
I'm not sure, I maybe missed some place. My question is, so have you seen the selectivity change, I mean getting worse when carbon deposit goes up to ethylene from not ethane?
Selectivity to ethylene?
No, ethane, I'm sorry, all the way to the ethane.
We don't see that unless you allow the catalyst to run for a very long time in which the carbonaceous deposits, you reach a point after a long time in which carbon really starts to kill the reaction. So we had a deactivation, and then we had kind of a linear regime, and if you let it run for a long time, you'll have a final deactivation in which the catalyst just seems to die.
How long does it take?
2 to 3 weeks, running 8 hours a day, 8 to 10 hours a day.
This is gas-phase reaction.
Gas-phase reaction.
You know commercially they do what temperature they usually run?
Yes, I believe it's around 70 degrees C.
Well, even some cases lower than that.
Yes.
Okay.
I'm not sure I understood. Is this initial rate or rate after? I thought you mentioned 6 hours, because if it is being deactivated, it shouldn't be time dependent. Because you form carbon, therefore this carbon will accumulate on the surface and the activity should decrease.
Yes. So that is time dependent. As you allow time on stream to progress, the activity decreases because of the formation of carbonaceous deposits. But
your rate expressions don't have time.
no. But we accounted for that by allowing for a correction in the activity back to a time at 6 hours. So that before we took any rate data, I have a standardized conditions which I took rate data, and then I took rate data after the kinetic data, and then using that I can approximate that back to the time at 6 hours. So that's how I corrected for carbon forming on the surface.
Palladium hydrogenation is very interesting because you get a dideutyl addition to acetylene if you ran over a certain low concentration of palladium on a lead carbon catalyst. I was wondering if you thought of looking at the deuteration, found out whether or not you did get just 2 deuteriums added across the double bond, and whether there was a difference when you changed the mechanism by changing the temperature, if that would occur.
I have thought about, but we haven't done it. That's a good idea. We just haven't been able to get to it.
Thanks again, Matt.
Thank you.